Good morning. So, I am going to get back to the demo on Laplace's equation. What we will do today is I will start with the same 5 by 5 grid, that is we will have 3 interior grid points. Last time I do not know whether you realized it or not, but we were doing Jacobi iterations, just so that you realize that I was doing Jacobi iteration, right. It was simultaneous relaxation, all the points were changed in one shot, okay, that is basically what was happening. We will also try to see whether we can do Gauss-Seidel, okay. So we will do that on a 5 by 5 system, and 5 by 5 grids basically, remember, gives you 3 by 3 interior grid points. So the actual system of equations that you are solving is a 9 by 9 system of equations. So we will do that with say with that 5 by 5 system, and then maybe we will try something larger, right. And for the larger one I will basically use a package, not package, but a program that I have already written, so that I do not sit down and we can do it manually. I mean, it does not matter, I can write the program here, it is not a big deal. Maybe even for the larger one I will just do it by hand, it is just averaging, right. Then if we have time today we will also do SOR. I do not know whether you have tried looking at SOR, right, but I already have a program written for SOR for finding the optimal omega value. It is not to aid in finding the optimal omega value, right. It does not actually hunt for it does not do an optimization, it does not solve an optimization problem, okay. So that is as far as that goes. The other thing is, if you have tried SOR, right, so that is, remember, it was over relaxation, but it was still successive over relaxation. It was for the successive iteration, that is for the Gauss-Seidel, okay. My suggestion is try to find out what happens if you use a relaxation parameter with Jacobi iteration, just for the fun of it. Just see what happens if you try, right, if you try using a relaxation parameter with the original Jacobi iteration algorithm that we came up with. Is that fine? That is okay. So just try to find out what happens, and we will revisit that question, what I just suggested now, we will revisit it a few weeks from now. I will come back to that point a few weeks from now, okay. So I am starting off IPython. When you use it, of course you do not have to do this no color stuff. I mean, I am doing no color simply because the red that comes here does not come out well on the video, okay. That is the only reason why I am shutting off color. I just wanted to show you that as a difference between last class and this class, just so that we do not run into any confusion. Okay, so we will set it up quickly. So let me just to, so that is the plotting utility, and this package Mayavi, just so that you know, is built on top of another package called Visualization Toolkit, which is a C++ package. So if you want to access any of these 3D plotting utilities, functions, right, either in C or C++, you can easily write a program and tie it to the Visualization Toolkit. It is called VTK, the library is called libvtk, okay. I will just type it out so that you know what it is. I am not going to, the library is called libvtk. What Mayavi does is it places a layer of an interface between Python and the VTK toolkit, the visualization toolkit. That is basically what is happening. So all the visualization, because I had a question in the last class about visualizing what tools do we use if you are writing programs in C and C++ and so on, right. So fundamentally all the visualization programs are basically written in C, C++, Fortran, right, and what you see here in Python is normally a Python interface to an existing program in Fortran. So there are a lot of packages out there that you can use, okay. So GracePlot, for instance, is a front end to something called Grace, which has a history of its own, either XMGrace or XMGR or whatever it is. So you can try to interface directly to Grace, okay. You can try a package that I like to use is called YGL. I will just type it again, because this package basically tries to emulate the Silicon graphics library called GL, right. So which is very easy to use. So you can try, I mean, as I said, but there are lots of packages out there that you can use. And finally, of course, as a suggestion, if you can put a dot on the screen, and this is relevant to what we are doing on this course, right. So this screen that you are seeing right up front is what I am using on my laptop is 1024 by 768 dots. If you can put a dot on the screen, you can draw a line on the screen, you understand, and if you can draw a line on the screen, you can plot. Okay, is that fine? Okay, so there is always ways by which you can plot, right? There is always ways by which you can plot. Maybe in a later class I will show you, do a few demos of various plotting packages that you can use and so on. Okay. The other part, as far as programming goes, before I get into the demo itself, because of the nature of this course, you are writing all your programs in, right? I encourage you to write your programs in C, C++ or Fortran and so on. But when you eventually get to code development, right. So the way I do my code development is very often I start my initial code development in Python, is that fine, right, and then as and when, so if I have my program functionally correct, right, the program is functionally correct, you understand what I am saying, it functions properly, then I start through a process of writing either C routines, Fortran routines or C++ routines to replace elements of that Python program with something that runs faster as required. So as a consequence, I am able to sit, when I am in this process, I am always able to interact through Python, interact with my program, it is always interactive. And if it is batch, then I use my Python again to write a script to run the batch program, that is the idea. So in a sense, using Python as a programming language to steer large programs, that's what you are looking for, that's the ability that you want to get to, right, at some point in the future. But right now my suggestion is, if you want to try to do that, but my suggestion is keep writing programs in C, C++, Fortran until you make sure that you are totally comfortable doing that. Okay, let us get on with it. So I am going to import numpy because I need an array, right. So just like last time, I will create a 5 by 5 grid going from 0.5j. I think by now the syntax is most probably, I hope, familiar to you. 0.2, 1.2, and that should create for me a 5 by 5 mesh. Okay, that should create for me a 5 by 5 mesh. Those are the two things that we looked at in the last class. And of course, as a consequence, just like I did last time, I will say phi is x star x minus y star y. Okay, right, and we will set to 0. Okay. And of course, at this font size it looks a bit funny, but you can see that did I do the right thing? Phi of minus 1 comma 1 colon 1 minus 1 colon. Oh, sometimes, and since that does not make sense, we will do the right thing, right, which is what I was telling you. This is what I was telling you. The reason why I do this is, yes, I make mistakes, we all make mistakes, right. So I am not trying to make it perfect. Now you can see that all the interior points are 0, it is fine. Okay, let me just type up, because this helps me at a later point. So phi of 1 colon minus 1 comma 1 colon minus 1 equals, what is it? So today I will get a little lazy, 0.25 times what we have, zero colon minus 2, that shifted to the left, plus shifted to the right plus shifted up or shifted down plus that's shifted up, fine. So that in fact will give me the first iteration, okay, is that fine everyone? So we can go through this iteration. What if I wanted to do Gauss-Seidel instead? So we can go through this iteration. What I will do is I will just quickly redo this. So I reset my phi, I set it equal to 0, okay, because I need to store my error shall I say Jacobi equals that, okay, fine. How many iterations shall I do? 10 iterations, 50 iterations, 50 iterations. Or let us do 100 iterations just to be I in range 100, okay. I hope I have got everything right. So I will just copy that out, see if that works. Whatever has to be deleted we will delete, okay. Error is x squared minus y star y minus phi I, is that fine? I will just square it, I will take the sum. So ERR dot append fine. I could possibly even take the square root of that, np dot square root, sum of the squares, is that fine? This should give me what I want. And did I make a mistake? ERRJ. So when you get clever, that's what happens. ERRJ. Let me set up my phi again. Please bear with me. ERRJ. Okay, that's fine. Okay. So ERRJ seems to have a lot of zeros and way up there somewhere. So obviously the suggestion for 10 or 15 iterations was pretty good suggestion. And the interesting thing is that the error afterwards is 0, is identically 0. Okay, so it's actually possible that 2 iterates get the same, it converges to the same value. You need to think about what that means in this context. So what about Gauss-Seidel? I want to do Gauss-Seidel. What would Gauss-Seidel give me? I set phi as x squared minus y squared. So let me create a ERR G for Gauss-Seidel. I set phi is x squared minus y squared. I set make sure that the initial guess is right, okay. And in Gauss-Seidel what changes? Something here changes. So in Gauss-Seidel I can't do that phi I, I can't do that one whatever blah blah blah. So I have to I have to actually iterate through the whole thing, right. I have to actually iterate through the whole thing. So what I will do is Oh, Krishna. What I will do is, let me just type it up. For I in range 100, yeah, what do we want to do now? For j in range 1 comma 4, for k in range 1 comma 4. You have already done this. This is most probably a hassle, but anyway it is okay. Phi of I comma j equals 0.25 times phi of okay. As I said, this is most probably the last time I will bother you by writing this j comma k. I have to say wake up Ramakrishna. J plus 1 comma k plus phi of j minus 1 comma k. Yeah, you will have to plus phi of j comma k plus 1 plus phi of j comma k minus 1. Is that okay, everyone? And it is updated. I am using the same array, so it is updated immediately. Okay. So that is as far as that loop is concerned. Do I need to do anything else there? I do not need to do anything else there. So that is for the first for loop, that is for the second for loop. So ERR equals x star x minus y star y minus phi I am just copying from above. As I said, just bear with me. I do not want to make a mistake here. NP dot square root of what? Is that fine? Okay. So now we can plot these two and see what they look like. If you want to just see ERRG, a lot of zeros. Okay. Now we can plot these two. So from grace plot, I import my grace plot. I create the plotting utility. Cancel. And what do I want to plot? G dot plot. Okay. Two things look very similar. As I have always said, use a log scale. So go to a log scale, apply. I do not know why it went to 10 power minus 4, 1 e minus 16 even 10 power minus 16, it seems to just okay, fine. And as I had indicated earlier, Gauss-Seidel converges faster than, right, Gauss-Seidel converges faster than Jacobi iteration, and it sort of, if you squint at it, it does look as though it is twice as fast. On a log scale, the slope does look as though it is twice as fast. Is that fine? Is that okay? Right. So I am not going to say how far down it goes, it is going to suddenly drop to 0, right, that was very clear. So one of the things, of course, what I normally do is I do not just allow the program to run in the background, I usually plot this graph while the program is running, so that you only look at the graphical output rather than, what I will do is, why don't we run a 101 by 101 or something of that sort, we will run a big one. learn a big one. So I will recreate this. So I will just basically say x comma y is 101. What do you want? 101 is fine. 101. 101. So that gives me a 101 by 101 grid. Okay, and everything else should actually work as it is, because there is nothing in there that was specific to the number of grid points, except for the Gauss Seidel we have to be a bit careful. So what I will do is I will make this E R R J equals, I will just overwrite it, it does not matter, or maybe we can make it 101 either way, and go back to the Gauss Seidel. I am sorry, Jacobi iteration. So that should do Jacobi iteration for us. Is that fine? J should be 101. Is that fine? Thank you. Okay. Okay. Any questions? Something?
Why did the x and y matrix? I mean x and y. Why does M grid work? Why do you get such a matrix? One where in column 0 to 1 and the other one rows.
Well, they basically, if you think about the xy coordinate system, at any given point, I have an x comma y, right? So that M grid is essentially generating for me the array of x's and y's that represent the mesh underlying grid. Does that make sense? I can go to the board, maybe, it's fine. We will see if it shows. Yeah. So essentially what we are doing is, no, it's fine, it's okay. Essentially what we are saying, is, so this is 0 comma 0, this is what I am generating, right. So this is 0 comma, in this case 0.333, 1/3, 0 comma 0.66 approximately, right. So the x matrix consists of all the x's and the y matrix consists of all the y's, right. So if you are somewhere in between, so this would be 0.66 comma 0.33 and so on. So the x matrix consists of all the x entries and the y matrix consists of all the y entries. Okay, that is basically what it does for you. Is that fine? Right? Yeah, sorry about that. Anyway, so let us get back to this. I think this code is fine as it stands. So if I run this now, it should give me okay, and we did this 100 times. Is there any chance anything would have happened 100 times? Do you want to run it longer? Okay, why don't we repeat the process? I will just make this G, repeat the process for Gauss Seidel. And Gauss Seidel, you remember I have to change quite a few things. I have to make this ERRG 101 and I have to change the limits to 100. Is that fine? Okay. And that takes a little longer, because now we are sort of looping through. I am not using the inherent iteration capabilities of NumPy or the matrix abilities of NumPy, but doing it myself manually in Python. Okay, so G dot plot ERR J101 data has non-positive values. What happened? Let's try ERR G. Maybe I made a mistake somewhere. Yeah, both have non-positive values. What is X? X is a 101 by 101 matrix. I just wanted to make sure that was right. How is that possible? How is it possible for square root to get a non-positive value? It doesn't make sense. Let's try that one more time. Make sure I have not made a mistake anywhere. I have initialized 5, I set it equal to 0. We will do 1000 iterations, but of course that shouldn't make a difference. Just in case there is some issue there, I will just do that. As you can see, even 1000 iterations, if you use NumPy, it is quite fast. And let me plot that just to make sure that I am not going to, if I am going to get the same thing, then we will just have to go on. Data has non-positive values, I still do not get it, but anyway it is okay, it does not matter. The point that I want to, really the critical point that I want to make out here, right, is first the blue line, which is Gauss-Seidel, does seem to converge faster still than Jacobi iteration. One thing good, but the bad thing is, which is what we expect, that the rate of convergence is quite slow, right. Look at what 5 by 5 is doing down here, and look at what my Gauss-Seidel is doing up, Gauss-Jacobi is doing up there. It is going to take forever for it to get down to a small enough value, that is 10 power minus 6 or 10 power minus 16 is what we did in the other one. Am I making sense? Is that okay? Right. So the convergence is actually extremely slow. So just as a let me do then a I will just restart this just to be clear that there are no threads running and so on. Let us just now do SOR or something of that, something a little different, okay, right, and we will try to see whether we can animate the code while it runs. So from maybe I could have done it with the earlier thing, but it does not matter. Okay, just to be fine, right, okay. We'll do, maybe we'll do one other thing. what we will do is we will see how these iterations go. I just wanted to show you that in the last class I used Mayavi to draw contour plots. I just wanted to show you that you can actually do surface plots. Okay, so why don't I just do that? So I am going to redo the 101 by 101 grid. I created the 101 by 101 grid, right? Phi is x star x minus y star y. I don't know how many of you have tried using Mayavi so far, but it's relatively straightforward to use. So what I do is I say V equals mlab dot surface x comma y comma phi. This is to show you what the initial solution looks like, and that should generate something that looks like that, and you're like, what is that? Now one of the things that I like about Mayavi is that you can interact with it. Okay, so let me maximize it, or maximize it. Okay, I'm going to add a legend to it. Show legend, so that we can see what it is. So it goes from -1 to +1, and the coordinate system is at the bottom left hand corner. If you can't see the coordinate system, I'll make that larger. Okay, the coordinate system is at the bottom left hand corner, right? Fine. So this is the solution that we are expecting, right? So if you are saying, wait a minute, what is this? What is this? Okay, let me put an outline list like I did last time. And as I said, the thing that I like about it is that you can interact with it, right? So you can see from where the coordinate system, or from the fact that the solution is 0 0 at this far corner, tells you that x equals 0, y equals 0 basically, right? So and along this diagonal x equals y, so the solution is 0. So here it is a positive value, right, and here it is a negative value, fine. It goes from +1 to -1. So what happens when I set my solution, when I initialize the solution, that is the final solution, that is what we are supposed to get. Okay, if I just so that you see what is happening here, most probably you already know what is happening. I set it to 0.0. That is our initial condition. Okay, our initial condition, except at the boundary where it is x squared minus y squared, everywhere else it is 0. That is our initial condition. Is that fine, everyone? Okay. So now that we know that Gauss Seidel and Jacobi, we can actually see the solution evolve. So what we will do is, I will say let us do Gauss Seidel, let us do Jacobi. Okay, for I in range, Jacobi is faster, right? Gauss Seidel is slower, which for the sake of a demo is better, but anyway, how many iterations do you want me to do? At the rate at which it was going, most probably 5000 iterations or something is most probably whatever, 5000 iterations. Okay, fine. Let us see if we can find the Jacobi. Control R P H I, I will just search back. Okay, that is Jacobi iteration. Is that fine, everyone? Okay. So and I am going to plot only the phi. So we have computed the phi, V dot mlab scalars equals that phi. Let us run it, and you can see the solution evolving, and my computer is having problem. It is not going to rescale till I get to the last version. Okay, that is fine. So all you can make out, so this 5000 is quite a lot. All you can make out is that flat portion seems to be diminishing at a rather slow rate, and it is really going to take for almost ever. In fact, on the video itself, I don't know whether this will be visible. This is going to take forever to, it's going to take forever to converge. So it looks like even 5000 may not quite make it, right? You can see that little gray spot in the middle. You can see that little gray spot in the middle diminishing, and it's going towards the solution. Remember, this is Jacobi, right? Gauss-Seidel will basically run twice as fast, okay, and that's basically it. So essentially, the thing that you can do is that you can visualize, as I said, maybe I shouldn't have minimized it, but you can visualize this code running. As the code evolves, it's actually possible for you to look at the solution, right? And remember that just because on the screen it looks close to the solution does not mean that it is close to the solution. The screen resolution is very small. Is that fine? Okay. So these are some skills that possibly I am only showing you the tools being used. These are some skills that I think you should try to acquire, that you are able to visualize, A, that you are able to visualize your data, B, that you are able to do it while your code is actually running, right? There are sometimes, especially if you are going to do it with a scripting language like Python or something of that sort, there is a certain advantage to being able to interact with the code, that you allow it to finish executing a certain number of time steps or a certain number of iterations or whatever it is, and then come back and interact with the code, okay, fine. So that patch is almost gone. So actually at 5000 it seems to be quite close. Maybe 5000 was on the large side. Anyway, let's see. Fine, okay. Meanwhile, are there any questions? Let me see if I maximize this, whether it will, if I give it time it will. So even if I try to interact with it right now, because because it's completely tied. If you think about it, 101 by 101 is a 10,000 by, it's 10,000 unknowns. We are solving a 10,000 by 10,000 system, and we are doing 5,000 iterations. That's a lot of calculations. So it's also a good idea to do the computation as to how many operations we are performing beforehand, before getting into it like I just did right now. Maybe I should have just said 1000 instead of 5000. Anyway, it's okay, it doesn't matter. It should be close to completion. So the other point of course is that if you try to do this 5000 iterations directly in C, if you have already done this, you have most probably seen it's a lot faster than this, okay. So that's the big advantage of doing it in C or C++ or Fortran. So you pay a price for the ability to interact with the code. I am tempted to just kill it, maybe I will just kill it, okay, fine. Let us get back, we will start Python again. Now we will do, we have just enough time to do SOR. So I have a Laplace equation solver that I have already written, and SOR basically what it does is it is going to run SOR for me for that Laplace equation solver. Right now it is hardwired for a 41 by 41 grid, okay, it is hardwired for a 41 by 41 grid. So I will create a something that will run SOR for me, okay, and it has very simple way to do it. So what does this do? Let me what does run SOR do? What am I doing? What run SOR does is it is going to run SOR for the values going from 0.0 to 2 point, right, and I am taking 20 values in between. It is going to run for 20 values and it is going to take 10 iterations. Is that fine? I think I have really worn you guys out with this. Anyway, okay, let us see. let me just run it and see what we get. And this S has an error which is the error versus omega, right. I have S has an omega, those are the omega values that we ran, and it has a set of errors. Is that fine? Okay, right. So I will import just to plot it. We will just quickly do this. Okay, and plot there we go, right. And anytime we are plotting error, we really need to, this looks relatively flat, okay, this does not look that encouraging, but then we go to the power of the log scale. Anytime we plot error, we always look at it on the log scale, it does not look that flat now, right. So it looks like whatever we are looking for, this is important by the way, so you have to look at it in the log scale, whatever we are looking for, the optimal omega value that we are looking for is somewhere there. Is everybody with me? The optimal omega value that we are looking for is somewhere there. So let me hold that graph because I want to plot on top of it, okay, and I will create another SOR solver for me, okay, but okay. Let us go back to that graph. Now I want to hunt, I want to try out another set, okay. So what value shall I take, what values of omega, where shall I hunt? If I look at this graph, where shall I hunt?
1.5 to
1.52, well 1.2 you know is not going to do it, 1.5 to 1.9 maybe, right, is conservative. Bear in mind when you are doing this that the convergence that you have is non-uniform convergence, that is what we want, okay. So this limit is going to drift, right, does that make sense, does it seem, does that, or it is just going to continue down. So 1.92, so I say omega, I will say W np dot, I will create a vector, the syntax is very similar to mgrid, from 1.5 to 1.9, and maybe we will take 10 samples instead of 20, okay, 10 samples, okay, and I will create another SOR solver, and pass it this omega. So S1 should run 10 iterations, S1 should run 10 iterations for, and S1 also has an error, so I will plot where is my plot, S1 dot omega versus S1 dot error. Well 10 iterations, what did you expect, I mean it is going to be this, it is going to be the same thing, the only point is that the curve is smoother because we have more points, that is all that has happened, okay. So I fortunately I can go more, right. So I have a, it will go for a little more time, I have a little go more which will go for a little more time for 10 more iterations. So and if I do that, okay, then I can plot that again, and what do I get? Aha, so it is better and it is a little sharper, so it seems to be somewhere there, okay, it seems to be somewhere there, is that okay? In fact what I will do, I will get rid of some of this part, or let it is okay, I get rid of some of this part, so do not need, okay, it does not look as sharp because I have removed that part, but right, so it seems to be around, what do you say? Well yeah, I will be conservative still, 1.65, okay, that is 1.7, 1.65 to 1.85, why risk it, okay. So now I go back and I set this from 1.65 to 1.85. I am doing this because this is a demo. I mean, what you would do is you would hunt for it, maybe use bisection or something, you would hunt for it in a more systematic fashion. There are other ways by which we can do this. So now I will create a S2 so that does only 10, that's no good. So we will do an S2 go more, and we will plot S2. As you would expect, it is the same, you have done it twice, it is the same, it is a smoother curve. We will do it some more. Fine, okay. So you can see it is getting tighter and it seems to be around between 1.75 and 1.8. So it is possible for you to actually hunt for an optimal omega, right, and trust me, this curve here is not going to move that much, okay. If I were to plot, if I were to do just for the fun of it, if I were to run S, remember our friend S, there are 20 of them, so it will take a little more time. Maybe I will do it twice because I did the other one twice, okay. If I were to plot this, but you do not know what happened. Okay, that is what you get. So it is very clear that when I say optimal omega, it is truly optimal omega. And look at this, look what is happening here. You picked a value because you took 20 samples, you picked a value there, you picked a value here, the optimal is actually somewhere in between. Optimal is actually somewhere in between. Okay. So you can look at this and be under the notion that it is at 1.6, actually it is not at 1.6, it is because of the way that you are taking samples, okay. There is an idea, see you are looking at it and with your eye you are actually doing some kind of finite differences, right, you are looking at it is increasing here, decreasing there, you are looking at slopes, you are doing derivatives in your mind, and you get the impression that the minima by setting the derivative to 0 is somewhere here, but actually it is somewhere to the right. And because of non-uniform convergence, it looks as though it is drifting to that, it is drifting to one side, okay. So the hunt for the optimal value of omega has to be done a little carefully, right. But if you are going to make production runs, I am going to make lots of runs, I am going to solve this Laplace equation for different boundary conditions, I am going to do 10,000 different boundary conditions, then spending time finding that optimal omega makes a big difference, because where here you are still at 1 point something, this is at 0.01 something, right, in fact it is 0.001 something, am I making sense? This minimum here, just to give you an idea, is at 0.003, at omega equals 1 it is at 0.3, please remember it is a log scale, at omega equals 1 the residue is at 0.3, at omega equals 1.8 or 1.75 the residue is at 0.003, it is running 10 times faster, it is converging right now, it looks like 10 times faster, is that fine? Okay, and I casually made a suggestion that if you are changing boundary conditions, that you can find the optimal omega and find out and solve for the various boundary conditions, right. The question that you should pop to me immediately is, how do you know that the omega does not depend on the boundary conditions? Do you think that the omega will depend on the right hand side, the optimal omega will depend on the right hand side, or does it just depend on the matrix A? If you are solving Ax equals B using SOR, the question is, does the optimal omega depend on the right hand side, or does it just depend on the matrix A?
Yeah.
Think back to that graph that I drew, right, and the steepest descent idea that we had, which I mistakenly said Newton method at that time, the steepest descent idea that I had. Okay, fine. Okay, so I guess we will meet in tomorrow's class. I would suggest that you try out some of these things for yourself. Okay, we will meet in tomorrow's class. Thank you.